Hello everyone, welcome to my next tutorial. It is a sixth part of the solar cell application. In my previous video, we have already discussed about optical organic solar cell applications, optical absorption, rough interfaces, enhanced energy distribution, energy yield calculations, various topics we have already covered. In this tutorial, we will be discussed about the CT state, Exciton dynamics and impact of the parallel resistance in the same layer structure. Before start of my tutorial, I am going to introduce myself. I am Sahil Verma, application engineer of the well-known company Impulse Technology. When I started my tutorial, then I have already introduced my company Impulse Technology and their services. So who has not seen it my previous video, please check out the playlist. Firstly, we will be discussing small presentation, then I will be show how we can calculate CT state exciton dynamics and what is the effect of the parallel resistance when we introduce in the circuit. We are going to simulate in here CT state exciton dynamics. It means charge transfer exciton dynamics are the transfer of charge from one atomic site to another in a material. And exciton is a bound state of electron and electron hole which are attracted to each other by the electrostatic Coulomb force resulting from their opposite charges. Basically means I will be create a layer structure of the solar cell. Then I will be show the charge transfer exciton dynamics, how the charge transfer from one band to another band. In the similar structure, I will be introduce series or parallel resistance. Then we will be see the impact of the parallel resistance to the device efficiency as it tends to reduce the fill factor and the open circuit voltage. So in the Setfos, I will be create a layer structures solar cell with considering some of the layer. Let's move on the Setfos. Click at the right side and run as an administrator. About the Setfos, we have already discussed in my previous video how we can provide inputs, how we can create layer structure. It is the new version when Setfos provides or new features, then we can see it in the top here new version are available and number of the features are present. It is the Setfos GUI. For the create new simulation file, you can click at here. At here the file are zits, and if you want to save your current file, you can save as, and existing results are present in here. It is a passive optics modules, it is a absorption modules, drift diffusion modules where we can calculate electrical parameters, it is a emission modules, it is a scattering modules, it is a master equation modes. At here shift modes are present and they are optimization and emission zone fit. Number of the examples are present. It is a graphical inputs. At here script, it is a output console and results are present. Here we can create layer structure, and if you want to provide the so we can provide in here, and layer structure you can see at here. Setfos tutorials and manual are also given, so you can see at here. About the Setfos we have already discussed in my first and second video. Now I am going to create a solar cell application tutorial file. For the create new simulation file, you can click at here. For the better view, you can click at here. Basically, CT state exciton dynamics that generally means it is only possible to calculate the maximum achievable photocurrent. At here, connecting optical calculation with a charge transfer exciton dissociation and drift fusion model to possible take additional loss mechanism into account. Accounting exciton dynamics in organic solar cell to possible to reproduce current measure by the Galois research without according recombination efficiency below 1%. Firstly, we want to create at here layer structure. So you can add layer through the plus I symbols. Give one by one each layer name. Air, glass, ITO, PEDOT, P3ST PCBM. I am considering at here the similar files as based on the tutorials and similar data, so you can understand easily what is exactly I want to say in here. Surrounding. Now we need to provide at here the thickness, glass, and unit it will be 1 micrometer. It totally depend on you which value you want to consider in here. We have already created that same type of structures in my previous video. Top and bottom layer are semi-infinite medium, so thickness are irrelevant at here. You can see at here the layer structures. It changes according to the thickness. You can click at here to show the large view. Now we need to provide at here refractive index. At here it will be supported .nk file format. We are going to import at here refractive index file because which layer are dependent on the wavelength, so we need to import at here refractive index .nk file format ito.nk. Similarly for the PDOT, at here we are going to import PDOT Betron AL4083.nk file. P3STPCBM.nk file. For the aluminum, same we will be imports at here AL.nk file. We are going to calculate at here the electrical parameter as we have already discussed excitant. So we need to activate at here drift fusion modules and absorption modules, and we should be give the value of the electrode. Click at here the general tab for the electrode and enable it. It can be ohmic, thermionic organic and thermionic inorganic. We are going to calculate at here thermionic organic solar cell. Need to consider at here thermionic organic, and boundary condition or work function will be 5 electron volt. Similar for the ammonium, thermionic organic and 4.309. It will be same according to the tutorial. It totally depends on you which value you want. In between the electrode we need to import semiconducting layer. So in the general tab we activate semiconducting tab. If you want to import that here your semiconducting file for the excitant, we should be import that here p3stpcm.exe.am file and simply import that file. You can check out here the energy level, dielectric constant, all the value imports automatic. But if you don't want to import that file, so you can put your own data accordingly. The 5.2, 5.3 value you can change. At here we does not need to import at here the semiconducting files for the P3ST PCBM. We can also put our inputs. As for the energy level 5.3, it is a HOMO value, and 3.7 it is a LUMO value, and effective density you can change at here unit if you want to change at here. Dielectric constant at here 3.5. Doping and polarity are disabled for the current simulation. Optical generation efficiency at here 0, and mobility are given. You can see at here 5 into 10 to power minus 7 and 10 to power minus 8, like this. If you want to edit your unit, you can simply edit in here. At the next tab, it is a excitant tab. If you want to add more excitant, you can simply add, and if you want to delete, you can delete in here. In the excitant, you can see radiative decay rates, non-radiative decay rates are given. Unit totally depend on you which unit you want to consider. Generation efficiency will be 1. At here Langevin bimolecular simplified SRH auger SRH trap total are given. I am considering at here total. Diffusion constant it will be 0. Saturation limit are not considering at here. Annihilation rate are given 0. TT singlet generations. Exciton polaron quenching for electrons. Various tab are given in here. You can check. Optical generation efficiency. You can see it here 0.66. Pair suppression value 1.285 nm, and charge transfer type none, Onsgaard and Koster. I am going to consider at here Onsgaard and boron. At the next tab, at here trapping up for this material. Trapping disabled for the current simulation. In here mobiles ions for this material are given. For the anions you can see the value 1e minus 10, and for the cations you can see at here the similar value. Recombination for this material, we can activate that tab At here Langevin, Auger, bimolecular and simplified SRH are given. Recombination efficiency at here it will be 1. If you want to edit that data, you can simply edit according to your data. Photovoltaic I am not considering at here, and coupling you can see at here the charge Exciton.1. At the next step for the absorption settings, if you want to shift for single wavelength or energy, I am going to considering at here the step 5. At the below side you can check at here the preview graph for the intensity and wavelength. You can change at here the wavelength value 460 nm. At the next tab, drift diffusion setting. All the electrical parameters are calculated by this tab. You can check at here the mode, steady state, transient, AC impedance, intensity modulated photo spectroscopy and voltage spectroscopy. I am considering at here steady state. At the general tab you can see electrical source, voltage or current. Voltage will be 0 and temperature it will be 290 K. At here Kelvin and millikelvin are given. Transport types, number of the general tab are given. I am calculating in here exciton, so we need to activate that tab. It is the example for the solar cell couple exciton thickness. So now we need to activate shift setting to vary the thickness value of the active layer. You can check at here number of the parameters are given. For the electrical you can check layer, each layer and electrode. I am going to vary it at here P3ST PCBM thickness value. Simply select 10 to 150. Linear log, element log, random log list file as previous. Which data you want to and explanation are also given in here. Step will be 5. Now we can see that here the layer structure are completed. Absorption settings are also completed. Drift diffusion settings also completed, and shift settings parameter, which parameter you want to vary it you have already considered in. Now we need to provide at here your simulation file name, solar cell exciton, and simply click at here the play button. Now you can see at here the results, built-in voltage, current balance, device current. It is the calculated JD curve where D stands for the thickness of the P3ST PCBM. The comparison between the simulation and measurement of Galot as shown as the tutorial. With Setfos can also precisely quantify the recombination losses. If you want to change at here x-axis, log, inverse, so you can simply click at here. Exciton density, exciton rate, P3ST PCBM gain, and at here losses, power conversion efficiency, power density. If you click at here the play button, you can see at here the variation, LUMO, HOMO, charge generation, current, electrical field, exciton density, exciton rate, mobility, potential, and recombination. For the numerics, absolute, iteration, residual error. Photocurrent, stat contribution, photocurrent, reflected, transmitted. You can check at here one by one each layer. Transmitted color, absorption, layer absorption. For the glass, P dot, reflectance, reflectance for the S polarization and reflectance for the P polarization. Stat contribution and transmittance. As we see the illustration of the charge transfer exciton process, firstly it will be photon absorption, then CT exciton, and it will be divided at free charge carriers and the ground states. Free charges back to the CT exciton. Now I am going to see second parts, impact of a parallel resistance with the same layer structures. At an organic solar cell often suffer from short between electrode due to thickness of the different layer and the roughness of the substrate. The short can be often modeled as parallel resistance. The electrical circuit option of the Setfos allow to take this effect into account in this simulation. At here the drift diffusion modules are given. At the below side, if you move, electrical circuits settings are given in here. You can see at here the voltage, resistance across the series and the parallel. capacitance, lateral resistance. Each value are given. When we activate series resistance, you can provide at here the series resistance value. If you activate parallel resistance, you can provide at here parallel resistance value. Unit you can check at here: ohm, kilo ohm, mega ohm, microfarad. Number of the units are given. You can create at here your own electrical circuits. It totally depends on you which value you want to give in here. At here device area are also given. If you want to increase at here area, you can simply give at here value and change the units. Impact of the parallel resistance to the device efficiency as it tends to reduce the fill factor and open circuit voltage. Intensity modulated photocurrent spectroscopy of a bulk heterojection solar cell. I'm going to introduce at here only parallel resistance, so activate only that tab. Device area will be 1 and unit at here you can see. Parallel resistance value will be 20 kilo ohm. If you move on to the steady state solver, you can check at here Otto, Newton and Gamal solver are given. Random, Otto, current, continuity, relativity change, absolute current, number of iteration are also given. Damping differential equations are given. Now I am going to change at here the shift settings because we are going to vary it at here electrical parameter voltage. Range will be minus 0.5 to 0.8 and step will be 0.1. Layer structure will be same. Refractive index, semiconducting and photovoltaic. Absorption settings also will be same. We can simply provide at here new name, impact, parallel resistance and click at here play button. Now you can check out here the key figures: open circuit voltage, short circuit current, fill factor and maximum power density, power conversion efficiency, built-in voltage, circuit current, current balance, device current, excitant density, excitant rate. You can check out here one by one. Similarly, absorption, layer absorption, reflectance, stat contribution and transmittance. For the passive properties, you can check out here one by one each value, photocurrent and stat contribution photocurrent, absolute reducible error, iteration, recombination, potential, mobility, excitant rate and excitant density. If you want to compare the result with parallel resistance and without parallel resistance, you should be disable that circuit settings and give it here new name without impact parallel resistance and simply click at here the play button. You can see at here the variation. Power conversion efficiency without parallel resistance will be more, and fill factor open circuit voltage without parallel resistance it will be more as compared to the with parallel resistance. If you want to compare these data, you can easily compare with this. Click at here the solar cell impact parallel resistance and hold the control button and click at here the without impact parallel resistance. Now you can see at here the changes and without parallel resistance. We can see at here the comparison of simulated IV curve with and without a parallel resistance. So I hope you understand my tutorial. Now I am going to end at here my tutorial. If you have any query related to this, you can ask in comment box. My email are also given in the description box. If you want to book our demo, you can visit our website FluximAg or impulsetechnology.in. And who has not seen it my previous video, please check out the playlist. You can got a lot of the information about the Setfos GUI and number of the tutorial are given. Thank you very much.